Hi, this is Mrs. Vrobel. This is Chapter 8, Covalent Bonding, Part 5. So in this video, we're going to look at electronegativity to help us determine what's the bond type of the covalent molecule. And then we're going to look at polar and nonpolar covalent molecules. And then lastly, we're going to look at how do you determine the characteristics of a covalently bonded compound, mostly based on shape. Okay, so you may have heard the term electronegativity before. If you haven't, it's a measure of attraction that an atom has for a pair of electrons. So the stronger the attraction, the more likely the electrons are going to be pulled towards that atom. Electronegativity is actually a measurement of ionization energy. How easy is it to pull off that last electron? And also electron affinity. You might notice as you go across a period that the maximum of electronegativity typically hits at about 17, group 17, sometimes group 18. However, it does decrease as you go down a group. Okay, so this chart that I have here, and I'll share this with you, this is a measurement of electronegativity, and you might notice that the general trend is it gets bluest as you go from this corner all the way up to fluorine. And as a result of that, fluorine has the greatest amount of electronegativity. I heard a video describe that fluorine is willing to steal electrons from kittens. It's just so jealous of not having electrons. It'll take electrons from another fluorine. So the bluer the atom, the greater the electronegativity. And you might notice the gray atoms, those are atoms that their octet is satisfied, and as a result, there's no attraction from or with other elements or their electrons. Okay, so here is a chart that describes the shift in electronegativity. So this first set of curves right on the left here, this is the first period, and if you notice as you go across the period, the greatest is right here, which is fluorine. So fluorine, like I said, has the highest amount of electronegativity, and as a result it's the greatest at the top. So then this is period 2, then 3, and so on, and you might notice that as you go down the periods, the electronegativity decreases as a result. Okay, so how do you know what's the character of the bond? Well, we use electronegativity difference, or delta En, to tell us. So if you have two atoms that are bonded together, they're not going to have a difference in electronegativity, and as a result, we call it nonpolar covalent. Now, if you take the two numbers that are on that blue table and you subtract them, and it's less than 0.4, you would say, well, that bond is mostly covalent. Now, if it turns out that difference on that blue chart is greater than 0.4 but less than 1.7, we say it's a polar covalent bond. And then lastly, if that difference between those two elements is greater than 1.7 from that chart, we say that it's ionic. Okay, so this is just a summary of what I said. So notice the greater the difference, the more ionic in character the bond will have. The less the difference, we're talking about towards nonpolar covalent. Okay, so as a result of this, you might have like two children that are trying to share a toy, and one's pulling on the toy more than the other, and as a result you get unequal sharing. Well, that happens with elements too. You might notice in this chart that there's a shift from ionic to covalent, and we're talking about going from left to right. So as a result, the bond character shifts because of that electronegative difference. Okay, so polar covalent bonds, why do we care? Well, the interesting thing is when we have unequal sharing, there's a different level of attraction. One of the substances that you deal with on a daily basis, water, it tends to be polar covalent because the oxygen in the molecule tends to hold on to the electrons more tightly. So as a result of it, there's a greater negative charge towards oxygen. And then there's a partial charge of positive with the hydrogens. And as a result, we call this a dipole. So when you have unequal sharing of electrons, you have a dipole that results from that. Okay, here's an example of a dipole. So we have hydrochloric acid, and notice that the hydrogen has a slightly positive charge, whereas the chlorine has a slightly negative charge. And that difference is greater than 0.4, and as a result of it, it's more of a polar covalent bond. Now, please remember, when we're looking at covalent bonds, we're talking about either polar or nonpolar. Nonpolar typically occurs when the electronegative difference is less than 0.4, or we have two atoms that are the same element bonded together. When we're talking about nonpolar, and I'll show this in class, we're not seeing an attraction with an electric field. However, with polar molecules, we do see an attraction with an electric field. What does this mean? Well, the shape of the molecule actually can help us determine the polarity of the molecule. And typically, when we're looking at molecules, we're actually looking at electron pairs that are on the central atom. They actually help us to determine the polarity of a molecule. Here is an example where we have water on the very left here, and just to remind you, there are two non-bonding pairs of electrons on this oxygen, and as a result of it, there is a bent shape, and this bent shape actually makes it a polar molecule. Now here we have something totally different. We have carbon tetrachloride, and even though chlorine is negative, they are equally pulling on that single carbon, and as a result of it, there's an equal pull, and we see an overall nonpolar charge. Now, here we have nitrogen, and nitrogen has a lone pair of electrons on top of it, and here we have the Vesper, the bonds that are being pushed down as a result of that non-bonding pair. And as a result of it, we get an asymmetric shape, and we have an unequal distribution of the charge. So as a result of it, we have a polar molecule. Okay, so in summary, we're looking at the difference in electronegativity, and if it's greater than 0.4, we know that we're probably looking at a covalent bond that could potentially be polar. Polar bonds typically occur when electrons are not shared equally, like water, and as a result of it, we have a dipole. And then typically we're looking at the spatial relationship of the outer atoms, and as a result of that, we can predict whether or not a molecule is polar based on the presence of non-bonding pairs.